Okay, thank you. I will also talk in English due to our guests. My team is Electro-precipitation technology for nutrient recovery. I'm not the sole author of this presentation. It's actually our team member, Natasha Dudukovic, who is currently on another conference. So I'll be the presenter, so be gentle with me during the question section. So I will start with the idea of our project. In Serbia, as Mira said, we are the country that is still on the beginning resolving wastewater sector issues, and even within research, we perceive wastewater as only as a waste effluent, but as the currency is shifting, and we saw that the revised directive is urging for circular economy perspective in wastewater. We also started and wanted throughout this project to see it like this throughout this paradigm of circular economy. So we started several directions in exploring how we can contribute on a national level. At least our government, our ministry is responsible for wastewater sector, still don't recognize it as well. Only waste is considered within circular economy frame, but regarding wastewater treatment, sludge will be the first priority because we expect the increase in the amount of produced sludge when the infrastructure is starting to be built. And Anita was mentioning the sludge treatment and how we can start to produce some resources there. Also, while sludge and wastewater are important in general, for Serbia, it's nutrients that are really interesting, nitrogen and phosphorus, because we are dependent on importing fertilizers. Almost all our fertilizers are important, even if they're imported, even if they're produced in Serbia. The resources are from the Europe, America, China, etc. Also, why is it important to retain the nitrogen? Because we invest a lot of energy in Haber-Bosch method, and then during nitrification and then nitrification returning back the nitrogen in the atmosphere. So we are losing in both sides here. And of course, phosphorus is now recognized as a critical raw material. So we really have to consider alternative sources of phosphorus, and the wastewaters are one of them. So this is a general technology of wastewater treatment, and we pointed some places where resources can be retrieved from the waste effluent. So what Natasha was trying to do throughout her research is trying to precipitate struvite from the sludge liquor. That would be the central point from the supernatant after the sludge treatment. That is something that we are now investigating a little bit, where we are now in that perspective. In Serbia, struvite is recognized in the sludge program only for wastewater treatment plants larger than 100,000 person equivalents, that it will be economically feasible regarding some conventional method of struvite precipitation, because you have to build reactors, so only larger plants will be able to implement that. And regarding the size of our cities, not so much of those treatment facilities will be possible to be built, but we in the research try to play a little bit with it. So what is struvite? My colleague, who is a chemist, 2 weeks ago asked me, Đurđa, what is struvite? It's magnesium ammonium phosphate. It is something that is actually can be found in wastewater treatment plant, but as a problem, because if it starts to precipitate spontaneously, it can lead to pipe clogging, as you can see in the picture. So if you have wastewater with a little bit higher magnesium levels of hardness that is a little bit bigger, you will be able to have spontaneous precipitation with ammonia and phosphorus that is already present in the wastewater. But what we want to do is to control that precipitation. And of course, most of conventional technologies for SmartWater production is chemical, and of course, it needs chemicals to be used. And Natasha wanted to try electrochemical SmartWater precipitation using magnesium electrodes as a sort of alternative, and of course to recover in this way phosphorus and ammonia simultaneously, nitrogen and phosphorus. And of course you can see the molar ratio is 1. So we will try to perceive our wastewater in that way. So what we did, what she did actually, is she used 3 different sludge liquids. The difference was in percent equivalent of examined wastewater treatment plant, which also influenced on the characteristics of the wastewater. And of course, she changed a little bit the variables throughout the process, such as reaction time, current density, etc. We will see the results later. And she wanted to examine whether she can precipitate the SmartWater in this time frame, in some sort of time frame that can be also economically viable. And of course, she examined the remaining, the quality of the remaining water, and tried to prove that she actually precipitated SmartWater. So these are the sludge liquor wastewater samples. You can see the differences. It's small, medium, and large wastewater treatment plants, and they differ a little bit regarding which wastewater it is at the beginning. So for the small settlements, it is mainly domestic wastewater, so municipal one. For medium, you have contribution of some smaller industry, mostly in the food sector, and some craft workshops. And the large one had larger input of industry effluent, mostly also in food sector and chemistry sector. Of course, all these wastewater treatment plants employed activated sludge system for secondary treatment and aerobic digestion. So we retrieved the sludge liquor for the process of electroprecipitation. And here you have the characterization. I know it is extensive, but at least we can focus on the nitrogen and phosphorus content. And it's important to remember that phosphorus content decreased as the number of percent equivalent increased as well. And it is interesting that you have a little bit of calcium in wastewater sample number 3 that will lead to also some side products regarding the precipitation. So the laboratory experiment looked like this. She used magnesium electrodes, in total surface of 46 quadrat centimeters, in a 1 centimeters spacing between them. The wastewater sample, sludge liquor sample, to be precise, was continuously stirred. We used room temperature. We did not performed pH adjustment or conductivity adjustment, and of course we cleaned the electrodes after each experiment. And as I said, she explored some kinetic parameters and tracked the concentration of phosphorus, nitrogen, and magnesium concentration in the remaining liquor. Of course, if it decreases, it means that all of them are precipitated in the intervals below. So we tried several time frames, applied current density initially of 25 amperes per square meter. Later we also played with that as well, and of course monitored the concentration. So I will be brief in the results. Of course, you have to bear in mind that you have the increasing phosphorus and nitrogen concentration as the percent equivalent is increased for larger plants. So you need, in general, more time to allow the anode dissolution of magnesium from the electrodes to reach the solubility equivalent. I think that's the right word, proizvod rastvorivost in Serbian. So the struvite starts to settle. For phosphorus was one to watch. You need, after 30 minutes, the phosphorus for sample 1 and 2 was removed over 95%. A little bit more time needed for sample 3 as it has more phosphorus and nitrogen, so more magnesium needs to be dissolved. And nitrogen concentrations did not change throughout the time frame so much. So the maximum that you can manage regarding its concentration reduction is about 40%. Of course, some other side components in the wastewater can play inhibitory effect in this area. So we check the magnesium concentrations when applying the current. So you can see, of course, over time it increases, and in one point it will start to settle as struvite. You can even make a correlation between optimum times for each sample. For first 2 it's 30 minutes, and for sample 3 is around 90 minutes, when the pH is actually the optimal one for struvite precipitation. It's about 8.4, and we think that those are the times when the struvite started to settle per each sample. So of course, current density also shortens the time of the whole procedure. Of course, you don't want to use high current densities because the electricity consumption is higher, even if you also exceed the time of the experiment. So you want to be as shorter as possible, but of course higher current densities cause magnesium to release faster from the anode and to start the precipitation. Regarding these treated samples, okay, higher the current density caused better removal or better precipitation of struvite, but it didn't differ so much. So you can stay in a lower current densities and have effective removal of nutrients in the sludge liquor and gaining the desired precipitate. And of course, here is also how current strength influences magnesium concentrations and pH values. Of course, it increases them, but you have to watch out on your optimum. So for sample 1 and 3, 20 amperes per square meter was optimal in our perception. In that time frame, over 20% of nitrogen was removed, but you can increase it, but then of course with higher current densities. And for wastewater treatment 1, the magnesium concentration remained unchanged, and in wastewater sample 3, more magnesium was detected, but in the initial samples we have the variation of the magnesium present. So I'll show later what were the cross-section of optimal conditions. So in order to better present the variables that we have, there's 6 of them, 3 wastewater tested. We can have a principal component analysis, or PCA, that easily visually assess the impact of crucial parameters. So we can see that the correlation of phosphorus removal and current density, and that is these two are influenced by one by other. they show very good correlation. Regarding the experiment time, there is a smaller influence of phosphorus removal, and for nitrogen you can see that really it's almost independent. It does not influence nitrogen removal so much, neither the current density, neither the time, but if we have to be specific, current density has moderate influence and time of the reaction not so much. And also another visualization that was asked from us, from the reviewers of this research, is Parsons correlation that gives you a good visual identification of the relationships between key parameters. Blue ones are positive correlation, red ones are negative one, and the size and the intensity of the colors in both sides indicates on the level and strength of the correlation. So also we can see regarding blue dots for phosphorus removal, it's one before the end, one column. We can see that there is a good positive correlation for phosphorus removal, both from current density at time. For nitrogen, a lot less. And negative correlations are observed regarding nitrogen removal and present nutrients in the sample as it is, probably because the relation of the concentration needed to start the actual precipitation of struvite. Phosphorus here is something that is more easily to distinguish the influencing parameters for precipitation. When the precipitation was performed, we had an idea to analyze the remaining water. As I said, it was liquid at the beginning. Usual practice on the wastewater treatment plant, when you remove the liquid from the sludge, you just put it back on the beginning of the wastewater treatment plant to start be treating as a wastewater. When we removed the nutrients, we did a little bit of examination regarding what we have, and it was pretty clear effluent, and we tested it for microbiological and chemical parameters and compared it to regulation of the European Parliament for minimum requirements for water reuse. In Serbia, we have several regulations that can cover this use. It's not still synchronized, but we chose one that is now still on rule, as to say. And regarding the results, we can see that in the first sample, you cannot actually use it for any irrigation purposes because you have BOD in higher concentration, so biological oxygen demand parameter was not checked to the limit was higher, so you really have to put this effluent back on the beginning of the wastewater treatment plant. For other two, they can be used for irrigation of non-food crops and food crops that won't be in direct contact with the treated water. So maybe mostly for producing feeding for livestock. So regarding precipitate analysis, I chose to present just part of the results. We managed to see what variables are best for each type of sludge liquor for every wastewater treatment plants, and we try to see how our results differ from theoretical one. We calculated stoichiometrically regarding initial concentration of phosphorus and nitrogen and magnesium as we needed, what would be the mass of precipitate that we produced, and we see a pretty good correlation for wastewater 3, probably because of the actual amount that can be measured, because that's the effluent that had most phosphorus and nitrogen to begin with, and most leached magnesium needed for the precipitation. So the correlation is back then. It's a bulky experiment in this way, but wastewater sample number 2 is a little bit, there is a more pronounced difference, and of course in wastewater 1 that is really poor in nutrients, the difference is the biggest. So we are satisfied with achieving theoretical maximum that we can precipitate. Also, to really prove that we had struvite, we performed X-ray analysis. Of course, in all 3 samples, struvite was identified as main precipitate, but also depending on what you had in the beginning, we had halite and sylvite because we had potassium and sodium present in tested liquor samples. Also in samples 1 and 3, we found new barite because in those samples we had a higher magnesium level, so these minerals started to settle because reached the solubility equilibrium first, and it is lower than struvite, so we have a little bit of intrusion of that mineral, but it didn't influence the struvite precipitation in a greater manner. And for wastewater sample 3 or liquid 3, I mentioned in the beginning that we had a calcium in elevated concentration in this sample, so we have the presence here of calcite and hydroxyapatite because also these equilibrium were reached as well. So what we can conclude when we see all the results, that the presence of other minerals will, of course, depend on the wastewater characteristic or liquor characteristic that you have in the beginning. And we played a little bit with quality of this precipitate. What is the potential to use it as a fertilizer? We have national regulation and, of course, European one. Regarding European one, we have the satisfying amount of struvite that we can say that can replace a certain mineral fertilizer and to be a good slow-releasing fertilizer. The regulation says it has to be at least 7. Our was between 8 and 20. There was no metals. Serbian regulation requires this specifically, of course, the European one as well. They were all below the detection limits, and of course, throughout the entire process, even in the remaining water phase, liquid phase, there was no pathogens. So they were all destroyed throughout electro-precipitating treatment. And we also tested the confidence that we need to say that something is a fertilizer, that is phosphorus, nitrogen, magnesium, and kalium. They are isolated, and we see theoretical value, and what we managed to produce for each sample of our struvite. So for 1 and 3, those samples 1 and 3, those experimental values were closer to theoretical 1. Of course, you had the addition of potassium because you have it in the initial sample. And of course, regarding this composition, you can say that we can try to compete with commercial fertilizers such as the ammonium phosphate, monoammonium phosphate, triple superphosphate, MPK, Đurđa in Serbian as well. And of course, it is good that here you have those other nutrients besides phosphorus and nitrogen, such as magnesium and potassium. what is the conclusion? That magnesium electrodes prove to be highly efficient and powerful for true-white precipitation, that we can actually manage something for now for municipal wastewater, but actual samples that we want to test are more richer one in nutrients that are industry effluents, and we now started to make experiments with those kind of wastewaters, mostly with wastewaters from the food sector. I think Natasha is just presenting that on the conference. Of course, optimal condition for phosphorus recovery varied regarding the size of the wastewater treatment plant, which of course influence the concentration. And this approach can be a sustainable solution, but we of course have to bear in mind the price of the electricity and the amount of electricity that we need. We will try in the future to see the solar system regarding electricity production, and of course to now evaluate through life cycle assessment to really be sure which approach is better for true-white precipitation, conventional or this one, so we can really have some sort of validation for this kind of fertilizer in agriculture. So thank you. Ja sam pobegla, kako sam rekla.
Ukoliko neko ima pitanja za Đurđu, možemo sa